Hello, Accelerated Chemistry students. This is Ms. Krista Foley, and this is your Chapter 5, Section 3 video notes all over atomic emission spectra and the quantum mechanical model. So let's talk about light and atomic emission spectra first. So let's talk about the nature of light. So by the year 1900, there was enough experimental evidence to convince scientists that light consisted of waves. So when we look at a wave to the picture on the right, the amplitude of the wave is the wave's height from zero to the crest. So that's going to be how tall the wave is. The wavelength, which is going to be represented by the Greek letter lambda, is the distance between the crests. So think about crests as the hills of a wave or the top parts of a wave, and the distance between the two of them is going to be our wavelength. So waves also have a frequency, and that's represented by the Greek letter nu, and it's the number of wave cycles to pass a given point per unit of time. So the SI unit of cycles per second is called hertz. And so what we did is we used the product of the frequency and the wavelength is going to be equal to a constant c, which we're going to know as the speed of light. So this is an important equation for you. So c equals lambda nu. And the frequency nu and the wavelength lambda of light are inversely proportional to each other. So as wavelength increases, the frequency decreases. So that should make sense to you because remember, wavelength is the distance between the waves and the frequency is the amount of waves that pass at a given point. So if you increase the distance between the waves, that means less waves are going to go past a given point in a given unit of time. So the nature of light continued with, according to the wave model, light's going to consist of electromagnetic waves. And these electromagnetic radiation is going to include radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. And all electromagnetic waves travel in a vacuum at the speed of 2.998 times 10 to the 8th meters per second, which is also known as the speed of light. So, as sun and incandescent light bulbs emit white light, which consists of a continuous range of wavelengths and frequencies. When sunlight passes through a prism, the different wavelengths separate into a spectrum of colors. In the visible spectrum, red light has the longest wavelength and the lowest frequency, and on the opposite side is violet. So the electromagnetic spectrum consists of radiation over a broad range of waves. So as you can see, red light has low energy, and ultraviolet has high energy. And when we look at these things, radio waves are going to be the least penetrating and gamma rays are going to be the most penetrating. So when atoms absorb light, their electrons move to higher energy levels. These electrons lose energy by emitting light when they return to lower energy levels. So when we talk about atomic emission spectra, a prism is going to separate the light into colors that contain. So white light is going to produce the rainbow of colors, Roy G. Biv. For elements, though, for example, this helium lamp, it's only going to produce discrete lines, and these discrete lines are going to be specific to helium. They're going to have a specific wavelength and a specific color. So the energy absorbed by an electron for it to move from its current energy level to a higher energy level is identical to the energy of the light emitted when the electron drops back to its original energy level. The wavelengths of the spectral lines are characteristic of the element, and they make up the atomic emission spectra of that element, and no two elements have the same emission spectra. So think about these emission spectra as fingerprints for different elements. This is how physicists and astronomers can figure out what makes up the stars when they look at their emission spectra. So let's look at an example how we can calculate the wavelength of light. So if we were to calculate the wavelength of yellow light emitted by a sodium lamp, if the frequency of the radiation is 5.09 times 10 to the 14 hertz, we're going to start off with this question. So let's list our knowns and unknowns because this is a mathematical problem. So we know that we're going to have 3 steps. We're going to use the equation C equals lambda nu to solve for the unknown wavelengths. So we know frequency, we know C, which is our speed of light constant, 2.998 times 10 to the 8th meters per second. And we don't know wavelength, and we're going to solve for that in meters because as you can see, both of our knowns have seconds as units, so we're going to be able to cancel those. First, we're going to write the expression that relates the frequency and wavelength of light. Then what we need to do is we need to rearrange that equation and solve for lambda. So C equals lambda nu So we get lambda equals c divided by nu. And to do this, we divided by nu to get lambda by itself. Then what we're going to do is we're going to plug in what we know. So we know our c, which is 2.998 times 10 to the 8th, and we know nu, which is our frequency, 5.09 times 10 to the 14th. Our seconds are going to cancel, so our answer is going to be meters, which is 5.89 times 10 to the minus 7th. Easy enough, right? So now let's evaluate. Does this make sense? The magnitude of frequency is much larger than the numerical value of the speed of light, so the answer must be less than 1, which it is. And also our answer should have 3 significant figures in it, which it also does. So now let's talk about Max Planck. Max Planck was a German physicist, and he showed mathematically that the amount of radiant energy E of a single quantum absorbed or emitted by a body is proportional to the frequency of radiation. So he came up with the equation that energy is proportional to frequency, or E equals h, which is his constant, Planck's constant, times nu. So Planck's constant h is 6.626 times 10 to the minus 34th joules times seconds, and joules is the SI, or the System International Unit for Energy, so you're going to see that a lot more as we get further and further into this. So after Planck, Albert Einstein came in, and he used Planck's quantum theory to explain the photoelectric effect. So in the photoelectric effect, electrons are ejected when light shines on a metal. Now, in the photoelectric effect, not just any frequency of light will cause the photoelectric effect, will cause a metal to emit an electron. Red light will not cause potassium to eject electrons no matter how intense the light is. However, very weak yellow light shining on potassium will begin to have potassium emit its electrons. So the photoelectric effect could not be explained by classical physics. So classical physics correctly described light as a form of energy. But it assumed that under weak light of any wavelength, an electron in a metal should eventually collect enough energy to be ejected. So to explain the photoelectric effect, Einstein proposed that light could be described as a quanta of energy that behaves as such as if they were particles. So this light quanta is called photons, and Einstein's theory that light behaves as a stream of particles explains the photoelectric effect and many other observations. So light behaves as waves. In other situations, we must consider that light possesses both wave-like and particle-like properties. So in this, what happens, depending on the wavelength of light, that will determine whether or not the electron will be able to be emitted from a metal. So let's calculate the energy of a photon. So what is the energy of a photon of a microwave radiation with a frequency of 3.20 times 10 to the 11th inverse seconds, or hertz? So first, let's list our knowns and unknowns. We need to use the equation E equals h nu to calculate the energy of a photon. So we know frequency and we know h, which remember is Planck's constant, and we're solving for E. So this is a simple plug and chug problem. We love these. So we're going to write the expression that relates the energy of a photon of radiation and the frequency of the radiation. Remember, that's E equals h nu. Then what we're going to do is we're going to plug in and solve for E, which in this case is 2.12 times 10 to the minus 22nd joules. We're just going to take 6.626 times 10 to the minus 34th, times that by 3.20 times 10 to the 11th. And let's make sure that this makes sense. So individual photons have very small energy, so our answer is reasonable because it's raised to the minus 22nd. So when an electron has its lowest possible energy, the atom is in its ground state. That has a principal quantum number of 1. So exciting an electron by absorbing energy raises the atom to an excited state with n equals something higher than 1. So the quantum of energy in the form of light is emitted when the electrons drop back to a lower energy level. So light emitted by an electron moving from a higher to a lower energy level has a frequency that's directly proportional to the energy change of the electron. So if we were to look at this, depending on how far the electron jumps to get excited and then falls back down, will determine what kind of frequency it has and what kind of wavelength it has. So there are 3 groups of lines that are in the hydrogen spectrum that correspond to the transitions of electrons from higher energy levels to lower energy levels. So if the energy level of the light is in the ultraviolet range, then you're in the Lyman series. And if it's in the visible range, then you're in the Bauman series. And if it's in the infrared range, then you're in the Paschen series for hydrogen. So given that light behaves as waves and particles, can particles of matter behave as waves? So Louis de Broglie referred to the wave-like behavior of particles as matter waves, and his reasoning led him to a mathematical expression for the wavelength of a moving particle. Like nature of matter. So today, the wave-like properties of beams of electrons are useful in viewing objects that cannot be viewed with an optical microscope. So electrons in an electron microscope have much smaller wavelengths than visible light, and these smaller wavelengths allow a much clearer enlarged image of a very small object such as a grain of pollen that is impossible to see with an ordinary microscope. So classical mechanics adequately describes the motions of bodies much larger than atoms, while quantum mechanics describes the motion of subatomic particles and atoms as waves. So Heisenberg, we've talked about him before. So he has an uncertainty principle. He states that it is impossible to know both the velocity and the position of a particle at the same time. So this limitation is critical when dealing with small particles such as electrons, but it does not matter for ordinary size objects like cars or airplanes. So basically what it says is that to try and locate an electron, you must strike it with a photon. So the electron is such a small mass that striking it with a photon affects its motion in a way that cannot be accurately predicted. So the very act of measuring the position of the electron changes its velocity, making its velocity uncertain. So basically, you can either know the position of the electron or how fast it's going, but you cannot know both. And that concludes your Chapter 5, Section 3 notes all over atomic emission spectra and the quantum mechanical model. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chem's 2012 edition of the textbooks, resources, CD, and pearsonchem.com. Thank you for watching.